Our next speaker is going to be Bartosz Szurgot, who is quite famous for going over time, so I'm going to be very brief. He is a veteran of both software and the Code Dive conference right from the very beginning. His professional focus areas include C++, Linux, and DevOps. Let's welcome Bartosz Szurgot.
Okay, so hello everyone. I see actually some seats are taken, so it means that someone will listen. Actually, I'm a bit disappointed because I was hoping to get to another session, but anyway, we'll need to proceed, I guess. Okay, so welcome to the structured logging. Before we jump into logging itself, let me introduce myself. So I'm Bartosz Szurgot. I'm a professional C++ developer working on Linux platform. I mostly develop server-side and distributed systems, also embedded systems. And I'm also interested in DevOps, security, algorithms, data structures, and probably half a dozen other things which are not really that relevant for this talk. But the funny thing is that actually it's thanks to Linux where I got my nickname from. In one of the companies I worked for, a friend of mine noticed that if you take two first letters of my name and two first letters of my surname and concatenate them, it forms a phrase bash, which is like a Polish written pronunciation of bin bash shell. And since I use bash a lot, then the kind of nickname just stuck to me. And people used to joke, if something doesn't work on bash, then I'll go to bash, ask him, and he'll fix it. So that's roughly how it goes. Okay, so before we jump into logging, let me actually give you an interesting tale of a sort of a character in a string. The task is fairly simple. String, just row of characters, and we are looking for a particular instance. So the example implementation can look like this. We have a string of C string of a known size, and we return pointer to the location. So we iterate over each and every character, check if the character is X, which is the character we're looking for. If we found it, return the pointer. Otherwise, return a null pointer to indicate that we have not found anything. And this is how the things have been done in the IT industry for probably well over half a century, which is probably longer than the IT industry is even called IT industry. So it's a hell of a lot of time. And everyone is doing this ever since. But now, what if I tell you that this algorithm can actually be improved? And what if I tell you that this algorithm can actually be significantly improved? Or what if I tell you that it's going to be ornithological presentation? Okay, kidding about the last part, but actually algorithm can be improved with a so-called sentinel pattern. So idea is fairly simple. We get exactly the same function signature, and instead of the terminating 0 at the end of the string, we put a character that we are looking for. Then we are iterating over the string, one element by another, but note that there is no boundary check here. So we remove one extra comparison every iteration of the loop because we know that the X is either in the string or in the sentinel location we have just added artificially. Then we restore the original null terminating 0 to just make the string look back as before the call. And then we check. If the pointer points to the sentinel location, it means we have not found X in a string, so we just return a null pointer. Otherwise, we return the pointer to the X we have actually found in a string. And poof, voila. It's that simple, right? Just a few lines of code, and actually you get 1/3 less assembly instructions per loop iteration. So that's actually something mind-blowing if you think about that. That actually took over half a century for humankind to realize that, because this idea is like a few years old. Andrei Alexandrescu was talking about that, I think, 2 years ago or so. So it's actually brand new. And the lesson learned here is that sometimes, even for these little obvious things, you might find a better solution if you actually think about that, because sometimes things are just too simple for you to realize that they can actually be changed. And today, in context of logging, are we going to have the talk like Captain Obvious style, just logging, everyone is logging, file line, and poof, off we go? Well, actually not really. It won't be an ornithological presentation, as I said. Today I'd like to actually to show you how logging can be done in a very different way than probably most of you are logging nowadays. By the way, how many of you are using Logger at their work, pet project, or whatever? Raise hands. Okay, well, at least half the audience, probably more. Okay, so one more story. Actually, this is my personal story, how the things began for me. Not so long ago in the corporate environment, not that far away, we had a system which was using a concept of node address. This was like a small network of multiple nodes. And because of that, we were just using 2 bytes for address, and certain bits actually had a meaning regarding the topology. So just by convention, we're writing the addresses down in hexadecimal format in the logs. So this was quite nice, because when you had this log text file, it was quite easy to grab through, and usually like 99% of the hits were exactly these node addresses that we are looking for, some other noise in between, but most of the catches were fine. So it was good. But actually, if you think about that, hexadecimal in a string formation can be actually denoted in uppercase and lowercase. So you actually need to do a grep case insensitive. Well, it's not rocket science, it's something you need to remember about. But the fun thing starts when you actually have a node address which is a very low number, because then you can have a leading zeros or no leading zeros at all. And as you can imagine, half of the world is doing this one way, and the other half of the world is doing it the other way around. And the shorter the pattern, the more false positives you'll get. But proceeding with this thought pattern, it turns out that many people just ignore the leading OX at the beginning because this is a node address, so it's obvious it's hexadecimal. Well, when you see a value of 42, it's not really that obvious. It equally well can be an octal display. So that's kind of a problem, right? But actually, even a hexadecimal display for some people is like this black hat voodoo magic that hackers do to hack other people's computer, so they prefer the decimal display. So you get some number which you can't really even see the bits out of it. And after preparing this list of exceptions that you need to be aware of in order to grep logs, I thought, okay, I've seen everything and nothing can surprise me. And then once again, I'm looking for a communication with a given node, and I'm sure it's there because I can see side effects of it, but I can't see logs indicating actually any messages arriving there. And when I finally found it, the value was minus 1470. And if you're wondering, this is a signed integer representation of OXFA42. And at this point, said like, okay, we're done here. There's definitely something conceptually going wrong, and the logs are just unreadable in this form, right? So today, we're going to talk about logging in a different way to avoid this sort of problems and actually many more. But what's actually on the menu? Because logging itself is a really huge subject, and you can have multiple elements, sections, that needs to be addressed. For instance, first there is log generation, so there is probably your system you're working on where you're generating, writing logs and pushing them to some other source. Then there is probably some stage which gathers logs through different parts of the system, maybe different components, and aggregate them into one common format, for instance, with Logstash. Then you push it to some service that will keep them and index them, for instance, Elasticsearch. And then you can analyze and visualize certain elements, for instance, using Kibana. Today, we'll mostly focus on the first part, so the log generation thing. So I'll actually show you how to create a client library that allows you to log reasonably and also to just to make a log analysis easier in the further steps. And the whole implementation will be in C++, partially because I like it, and the second reason is because I actually needed this implementation in one of the projects I'm actually two projects that I'm participating at the moment. But regarding this coding part, please keep in mind it's highly simplified. I allowed myself to ignore most of the optimizations, thread safety, const correctness, encapsulation, and probably tens of other things, just in order to gain the readability. So I just wanted to keep examples short to fit on one slide and just give you the rough idea how it works. So please do not raise hands when you see the place where move or forward could be used, for instance. That's just not the case in the slides. It's just about the idea. And by the way, you're welcome for that. Okay, so the first question, actually quite trivial in a way. What actually is a log? When I say a word log, what actually pops up in your mind? I would assume that for majority of people, something like this. So a big text file with log, one entry per line. And actually, this is at best the small brother of a log, because in fact, it's not really what log is. The log is actually a data structure. Let me repeat that. A log is a data structure. It is a data structure which contains events organized by time, so in the timeline, and it says absolutely nothing about the format of what is log or the content of the event per se. So this text file is just some handicapped representation of log at best. And there's actually a great book on the topic called I Love Logs by Jay Krebs, and highly recommend reading the book to you, and we'll get back to it shortly. But for now, for the sake of this presentation, we will just assume that whenever I say log, I mean system activity log. So again, for now, we'll assume that it is a partially structured thing that contains some common fields like timestamp, priority, maybe a process name, a thread ID, where it was generated. And then there is this message about what actually we are trying to log. And again, let's assume that this is a sentence in English. And this is somehow better approximation, but we'll actually get back into it shortly. But first, let's talk a little bit about the typical logger. So how the typical logger looks like. Well, in C++ world, it's very common to use the streams notation. So you have my log, which could be even a C log for the sake of discussion. Hello, the answer is something, the answer, and then some other string, I guess. The first thing, if you actually try to implement logger this way, you will notice that there is a problem. Where actually is the end of my log? Because whenever you are logging with streams, you have the effectively a function call to a stream operator with one parameter. And the question is it the first, second, maybe the last parameter, maybe we are somewhere in between? You do not know. You can do this with extra magic like temporary objects, doing things in destructor and this sort of things, but it doesn't really look that nice. So, but okay, this can be addressed. Another thing, how many of you can see a typo in this log? Please raise your hand. 1, 2, 3, 4 people, okay. Actually, typo is very trivial. There is a missing space after is here. It's a very stupid mistake, but actually, if you have this notion that you have a strings and then you put in parameters and then strings, it's very unnatural for humans to put the space at the end or at the beginning of the string. So people notoriously forget about it. And if you are actually having a string, then you are logging something that is a string itself, and then you have another string and no spaces in between. It's not really that easy to find out where's the beginning and where's the end of the words. So that's kind of not really nice. Now, the tricky part. What will be the output if we assume that answer is an integer and value of 42? Anyone? Assume that my log is just a cout. Okay. Yep, exactly. That's the funny thing, because it cannot be answered just like that. Because the possible implementation is 2a, missing space included, because the stream can be configured to output numbers in hexadecimal display. They can also be automatically prefixed with OX for hexadecimals, or they can be octal with a leading 0 or without it, and so on and so forth, right? So you can see where it's going. Just by looking at a single line of code, you can't really tell what will be the output of it, because it depends on a certain configuration of the streams. And the problem is that for streams, certain parameters are sticky, but some of them are not. Some of the modifiers you apply will only take will only be used for the next parameter, while the others will be there left forever and will always change each and every log that we are using. And this is actually kind of problematic. And the last thing is translations. If you have a sentence which is scattered with parameters, you can't really reasonably translate it, because in different languages the arguments might be located in different positions. And while some of you might argue, okay, why would I ever want to translate logs? Actually, there are systems when it's not really that stupid idea. I mean, like, all the logs is probably off the limit, because it doesn't really make much sense, but there are some logs that you really want to display to the user to signal him that something is going wrong, like for instance the most important, like error logs maybe, or warnings, this sort of stuff. And actually for many systems that have a localized user interface, it's actually a good idea to translate these logs as well, so that they can be displayed and fit in naturally to the interface. So for some systems this actually is a requirement, and you can do this with streams reasonably. So what's the alternative? Well, obviously, good old printf. So we have a formatting string, then we have a comma-separated list of parameters. And the interface actually has been added into C language in 1972, which is the year Alice Cooper released his Schools Out album. And as you can see by the poster, it's not really that new. And actually, the idea is even older. It roots back to BCPL programming language, which is rooted in 1966, as far as I remember. So the open question, what can be wrong with the IT interface that is over half a century old? Well, there can be actually a few issues. First, let's start with a bug. Anyone who sees the bug? Okay, around 5, maybe 8, okay, 10 people, okay. So roughly around 10, maybe 5–10% of the stage, of the audience, sorry. And actually the bug is a type. So here we are declaring that the parameter is a string, but here we are using answer, which on the previous slide we already said is an integer. So again, just by looking at the log, you can't really catch it easily, but this is a big problem. Because what you effectively do, you have a string which is a compile time known constant, then you have a parameter which is of a compile time known type, and yet you derive everything by just leave it back to the runtime to crash, or actually sometimes even work and just put garbage in the logs. And I call it accidental type erasure, because this is a type erasure, but you're not really intended to make it this way. It's just how it happens that the interface works. So not really a good way to go. Additionally, this interface has absolutely no support for non-standard types. So if you have your favorite class X or a point, how would you actually log it if it contains multiple members? You could obviously iterate over the members and just put one by one into log, but that's not really how things should go. It's not really scalable, it's not maintainable. So that's a really big problem in scale. Another thing, anyone tried to use printf with templates? When you do not know what type T actually is? Yeah, that's actually kind of big issue, because it generally prevents you to do any logging from any generic functionality, which in modern C++ is just a no-go. And finally, you might say, okay, there is this feature called variadic templates, which has been added in C++11. It's close to the good solution, but actually it is not perfect, because you still have the string for formatting, which is known at compile time, but evaluated at runtime. So you still can have bugs in the format that will only be detected if you effectively hit this line of code that you would like to have a log in. And finally, whatever interface you will choose for probably almost all the loggers that are there on the market, you'll actually get something like this. And we already said this is not really what we want to have in logging. This is not really what log is about. If you look at this, how would you actually express the query to get all the names of the browsers that users use? How do you extract all the 404 responses for the HTTP request? At the beginning, there is some structure, there is some date, some IP address, but after that, it's basically a string, and there is no format into it. And that's actually a problem. If these logs just come in like tens of megabytes or even gigabytes per second, you cannot just read it, you cannot process it. And what actually people usually do, they actually write rules, for instance, with regular expressions to parse the logs and then try to extract the information. So what you do, you have a fully structured information, then you pipe it into a text string line, and then on the other hand, you try to parse it again with regex or whatever solution is chosen. So this kind of sucks. And I actually have been at least once working in a legacy system where we were explicitly forbidden from touching any existing logs, because someone might be actually parsing that, and someone might be really expecting that the given regular expression will match to this particular line. And if you even say see some brain dead typo in the log, you cannot fix it, because if you fix it, you will silently break the other person's rules for parsing logs, and for instance, then the monitoring system might not react on your system failure, and this would be critical. So you can't really cooperate with that reasonably. So if you think about all these problems, probably some of you on the audience already have a feeling we might be actually solving the wrong problem here. Maybe it's not really the parsing of the logs the issue, maybe the issue is actually how we generate them. And I was actually in this thought process recently as well. And I started with bullet pointing what problems I would like to solve with a logger. So first, I would definitely would like to have a uniform representation per type. So whenever I'm logging a node address, it has one fixed representation, period, full stop, nothing more. You can't reformat it. If it is a node address, there is just one representation how it can be logged. Second thing, and probably the most important actually, is to make logs in a machine processable form. So you can then easily query against the log and check what's inside, and you can automate that. Of course, we would also like to have these nice features like user type support, so it comes in natural, not like this printf notation where you need to do everything manually. Of course, it needs to be easy to use, because it will require 15 template specializations to make it work. People will just not use it. And also, you don't want to have this stream problem with sticky configuration. So whenever you're looking at the line of code, you need to know exactly what and how will be logged in the backend. And of course, whatever is possible shall be checked at compile time. And as a side feature, let's allow also the system to be translatable, so that certain logs could be translated into other language for UI purposes. So, how do we actually define the expected output? Well, first of all, it needs to be structure preserving. So, the first idea, a tree. Why not? We'll have a root element that, for the sake of discussion, will be called just log. And all the nodes will actually contain either a key value pair, like for instance, a timestamp, bit, priority, or something more complex like a temperature, now, normal, and maximum. And because this is a tree, this is a representation that is machine processable and it is queryable. So now, if you think about searching for a log in logs for the entries about elements in your system that are overheating, you can actually query for a temperature and the nodes now that are greater than within a value than the normal. So if the value of temperature now is greater than the normal, it means we are overheating, and we can actually easily query for that. And what is actually overheating? Once we find these logs matching this pattern, then we can just ask, okay, so what's the element? And the element is CPU number 3. So we actually get all the information still in machine processable form. And that's actually a very powerful tool. But how do you represent that aside from the your own binary? How do you transfer it? Well, choose your favorite. You can put it in Bison, JSON, XML, YAML, whatever you like. For the sake of the discussion, we'll just stick to the JSON example so that we will have a uniform representation of the logs throughout the talk. But in general, that can be pretty much anything. And regarding the development, it's also nice to have this possibility to display the tree in a form of one line of text, because for development purposes, when you're dealing with really small piece of code, which will display 10, maybe 20 logs, it's perfectly fine, and it doesn't require you to have any sort of backend for logging to keep them. So this feature would be nice, but it's just bells and whistles in practice. Now, how do we map the tree into JSON or a similar structure? Well, it's brain dead straightforward, right? Because JSON actually represents a tree. So whenever you have a format that does represent a tree, the mapping is trivial. We're just going one by one and basically rewriting fields, including the structure involved. So that's really a simple job. Now, you might argue, okay, so I've just created a bunch of things and a bunch of theory around writing things to JSON file, right? My logger can also write to a JSON file. Pretty much every logger that is out there can write to a JSON file, but there actually is a difference. Like, most loggers will give you a JSON which will look something like this. Some regular fields at the beginning and then the message. CPU 3 is overheating, current temperature is, normal is, maximum temperature is, and that's it. The proposed solution actually will give you something that looks more like this. So again, the common fields are there, but now the element is separated as a CPU 3. There is a temperature which represents an object in JSON which contains a particular values. And while this English text, if you try to put it into computer, you will just cause some confusion, because computers are not really that good in interpreting human language. Even if they do try to solve this problem, it's usually still very error prone, and results are actually funnier than useful, and it still consumes a whole lot of CPU power to do so. So it's not really a way to go. But on the other hand, if you put a tree structure to the computer, okay, that makes computer feel like home, right? A computer can parse the trees, can iterate over it, can make queries against it. If you choose XML, there is, for instance, an XPath, so you have a standard way of expressing certain properties that you would like to for a certain entry to make, and so on and so forth. So that's very natural here. And this naturalness actually gives us a lot of possibilities. So first of all, we can do filtering. When we do filtering, we can also do statistics. So we can actually select certain logs and print them. And based on that, we can react. So for instance, let's say that we have an HTTP log that would look something like this. So there are some basic pieces of information about the query that has arrived, and at the very end we have a processing time in milliseconds. And when we have this, we can actually plot processing time against the timestamp. So we can get something like this. And we can clearly see that for a majority of the time, the processing is somewhere between 10 and 12 milliseconds, which is good. But then suddenly it starts to rise, and it's rising exponentially. And this means we actually have a problem in the system. And if we are observing this property, we can actually easily catch this with the automated rules. For instance, setting a threshold of how long actually this execution should take on average. And if it's rising, then we can actually react. How we can react? If this is a cloud-based system, we can, for instance, scale out. We can add multiple nodes to processing, and we can then observe if the curves gets flattened. If it gets flattened, it means we are back in the business because we are still able to process data as they come. If it doesn't, then add more nodes. And if finally the curve gets flattened, then maybe we can try to subtract some nodes and see if the curve still remains flattened, because maybe this was just a short spike because some news service reported that our portal is cool, and we need to and we just were experiencing a short period of heavy load. And this can be actually done easily with this automated set of rules. Okay, so now let's try to talk a little bit about the API. So first, on the client side, I'll propose something I call a simple log API, which will only contain raw arguments and have absolutely no explicit formatting. So example log might look like this. Log, timestamp, PID, priority warning. You can, if you like, put some optional text in English if you like, but it's not really needed here because all the information is preserved with a structure and named types. So you put a hardware element, CPU number 3, the temperature, which is a structure created of get temperature, so we are checking the current temperature of a node, and then putting in thresholds, and then you can log it. So it's actually quite easy for users to understand. Just put in parameters separated by commas, and that's it. And because you do not need to do any conversions at this point, it's also very easy for them to understand. Just put the element that can be logged, and poof, off we go. And thanks to this, we also have a uniform representation, because nowhere in this interface there is a way of changing how things are displayed. So whenever we are talking about the temperature, it will always get the same representation based on the type. And thanks to this, we also can get every element tagged, because if we know the type, then we can assign a tag to this type. And also, because we have a type, we can use C++ a type system and do argument-dependent lookup in order to find methods to actually, functions to actually parse this element, to put these elements into our tree, our internal representation. So the next type of sort of an API would be this formatted API, but we just said that we do not want to have any formatting, and this is still true. We do not want to have formatting that will change a display form. But actually, if you allow in a format only position of arguments to change, this will be actually good. And if you make this interface optional, it will also allow users to keep most of the log compact. So, for example, pseudocode for this can look like this. So first we have a string, which is our format, and then we have a set of parameters. So 0, 1 is first parameter, which is username Bob, then $2 and $1 is 42 and 2 consecutively. And thanks to this, you can actually change the order of parameters easily, but you cannot change a style. So the given value, if it's a type, if it's a username, if it's int, it will always be displayed in exactly the same form. And the most important thing, we need to make sure that this format here will be checked at compile time. And this is actually quite interesting how you can do this in C++, modern C++, and we'll actually have a separate section to address solely this topic. Now, you might say, okay, I've been always logging, and all my logs started with the timestamp, some PID, some priority, so like this usual fields. So do I need to do copy and paste around? And the good news is, no, you don't have to. And actually, there is a very interesting customization point if the logger exposes only the interface, which requires you to put all the fields in place. Because what you can do, you can create your very thin wrapper on top of it that will take a list of the arguments as a variadic template, and internally, we'll put all the fields that you are interested in, and then comma remaining list of the parameters from the user. So for instance, in a function name, you can, for instance, encode the priority to make the syntax even shorter. For warning, you'll get exactly the same set of parameters, but then priority warning, and again, arguments from the users. And this is actually a very interesting customization point. Why? Because when you're using a logger, some off-the-shelf, there are plenty of loggers out there in the internet, they usually provide you the given set of fields which is fixed. You always will get a timestamp, you always get a priority, but from that point on, it pretty much varies. So if you're doing a distributed system, for instance, an IP address of a node is a crucial important information for you. But on the other hand, if you're working on a single node, you do not need, or you do not want, in fact, to have an IP address, because it's always the same, it's just a pure noise in the log. So thanks to this, you can actually select what is your common set of fields that you would like to choose. So this framework does not actually impose any restrictions on you. You can have one field, you can have 20 fields if you need. That's okay. It's all up to you with just a few lines of code to wrap it for your particular project. Now the last thing is, obviously, we need to have some different destinations, and they will need to be configured at runtime. So this is actually trivial. It's probably all the logs that are out there. Loggers, sorry, will use it this way. So we'll have some base class here called a sync that will have a log method and a field info parameter. And there will be derived classes, for instance, a JSON file that will just write entries in the JSON form, one after another, into a text file, which is actually very useful for testing. So each test can log to a separate text file, JSON file. And then you can just see the logs and process the logs on a test-by-test cases. So if your test fails, and even if this fail is not repeatable for some, I don't know, random race in the code, you still have a log of this execution. You can have also a text console, as we said, sometimes useful for development, though not really essential. And for production environment, you can have a log stash, which will actually gather the logs throughout all the nodes in your system. So regardless of how big your infrastructure is, this will be the point that will be used for production purposes. But this is actually quite simple, and as I said, every logger does that, so we'll not really focus on this part. The only thing for you to remember is that the field info will actually be our internal tree representation of each and every logged element. So now let's talk a little bit about this log representation. So the logical view goes something like this. there is this field info, which logically contains two elements, a tag, which will be just a simple string indicating what actually is the element, and then there will be a value. And the value will be one of different types. So for instance, it can be a simple type like integer, double, boolean, whatever. Obviously, string will be a nice extension, and probably the most important element here is the vector of field info. So effectively, field info is keeping a vector of field infos internally. Why? Any ideas? Sorry? Yes, exactly, children nodes. This is actually how we form a tree. Each node has its own subnodes, and how do we actually stop this tree from going down ad infinitum? That's very simple. If we do not have this field info set, but we have any other field set, then it means we're in a leaf. So we actually have this key value pair at the end. So we can easily form any structure we want. And regarding the implementation, it's actually fairly simple. As we said, tag, just a string, no rocket science here. When it comes to different fields, we definitely do not want to waste space on them, so we'll use variant. If you are using C++ prior to 17, the boost variant will do. For C++ 17, std variant has been standardized, so it can be used. And then we just provide a set of types that we want to support, for instance, int, boolean, double, then the string, and then this vector, which will effectively allow us to form a tree. And let's call it a value. Now the last part is actually a member function called retag that takes a string and returns a reference to the object to self. And the purpose for it is to allow us to change a tag of the field info. So basically override this field in a nice and readable syntax. And we'll actually see it running in a second. Okay, so we just talked about the simple logger. So we effectively created recursive variadic template that use variants that can be traversed with overload set of lambdas. I guess that sounds something that might really scare off many people because it's not necessarily that easy to comprehend. But there are actually some good news. So even though that users actually see developers a little bit different than developers see the users, and usually the same applies to like developers who are using libraries compared to developers who write libraries. For instance, take a Boost or take a std library as examples. Then we can still actually provide quite a simple representation here, because this traversing of the tree is not really needed for users. Note that you only need to traverse the tree to actually generate the output log. So in order to write a new type of thing, you will need to traverse the tree, but that's it. From the user perspective, it's actually enough when a user knows how to create this field info. And here we can actually help. We can create a set of, just a convention of using two field info free functions that will take our basic types as parameters and will return already created a field info structure. So from user perspective, when user wants to create the log, add a possibility to log his brand new structure, for instance, a structure name which contains one field string, it is enough for him to create a free function to field info with the parameter of a name, and then return to field info as a result. And internally, we can use to field info name.value, which will actually call the overload for a string. And we already have that. So we actually have already working a piece of infrastructure for that. But there will be one little hint, because the string will be just called string. And this is not a string, this is a name. This node should represent a name, so it's not a random string. And this is where this retag comes into play, because now we can retag it with a name. So we can say, even though this by default is a string, please, for this context, retag it as a name, and poof, off we go. Now, let's try to do something more, some more interesting example. So a point 2D with two fields, x and y, so representing like coordinates on the screen, for instance. And again, we provide two field info with a parameter of point 2D and return type of a field info. And then we can create a field info. We can explicitly call it, this is a point 2D. And there is when the fun part starts. We are actually passing a collection of field info. So this is this part where this vector of field infos kicks in. And for px, we retag it as ox, and py, we retag as oy to indicate that this is x and y coordinate. So effectively, we create a structure that looks like this in memory. So we have this point 2D and two child nodes which contain the actual values. And if you look at it, this is actually exactly reflecting what the structure is. So we are converting structures which are known by the compiler at compile time into the runtime structures that we can later on use as a common representation for further processing. And this is actually quite nice, because thanks to this two-field info, interface is simple enough so that users do not need to tattoo it on their hand in order to remember what the hell is happening behind the scenes, right? And this actually composes very well. So if we take another layer of structure, for instance, a vector 2D, which is composed of 2 points in space, then again, we create a two-field info, which will take a vector as a parameter, and we create a field info. The tag for it will be vector 2D, and then we provide a set of field infos for all the fields. So again, we take a v-from, which is point 2D, but we already have a two-field info overload for point 2D, so it will be used. But if we have two elements which are called point 2D, this will actually be a problem, because we would not know in which point the vector is directed. So again, retagging comes into play, so we can retag it as a from and two values. So exactly the same name that we are using for the structure. So now the tree is a little bit more nested. So we have the vector, we have a from to, and each of them contains x and y. But we still preserve all the structure in place. So what we are doing is we are creating a structure, a runtime structure, which represents a compile time known syntax, and we have tags assigned to each and every node, including leaves. So thanks to this, we'll be able to query and search for elements. Now the second part of the interface, the formatting part, like this formatting that changes the order. David Grace once said that we should never put until runtime what we can do at compile time. And this is actually great advice that we would like to exploit here. So first, let's see how the interface could look like. So let's assume that we have a format structure, which is a template of an integer, and the parameter n indicates how many arguments the given format requires to make it work. And then the usual variadic template with the list of arguments provided by the user. So first thing we can do, we can actually do static assert check if the number of arguments passed by user is equal to the number of arguments which are expected by the format. So this will be our first line of defense here. If it doesn't match, then we just display an error, arity doesn't match, sorry, you need to fix your code. Either fix a format or fix the list of the parameters. Either way, it's invalid. But if it is valid, then we can actually process with the formatting, so we can take the format string, we can take the parameters and glue them up together to form one string that can be displayed to the user. Now, how do we do this string parsing? This is when const-x functions come into play in the form as they were presented in C++ 14. So we'll have a function format check arity, which will take a format in the form of const string known at compile time, and will return integer that will indicate the number of expected parameters. So we'll have a helper function called unique arguments, which will parse the format to return us the number of parameters in the format that are required, but a unique list. So if someone uses the same parameter 10 times, it is still counted as one. The implementation is fairly simple, so we'll just keep it like off the slides. And now we just check. If the count is 0, then it means format doesn't require any parameters. Off we go. We're good here. If, however, we have a parameters, we check what is the number of the highest ranked parameter, and then do a check if the count of the parameters is equal to this last position plus 1. And if not, then we throw an exception. And this is something that probably might cause a rise of the eyebrow for some of you. Like we said, we have a const-x function, and we throw an exception at line 8. So we, on one hand side, do things at compile time, but on the other hand, we have a throwing an exception. Anyone has any idea what happens? Does it even work? Yep, exactly. Actually, C++ standard is very explicit about that. You cannot throw exceptions at const-x functions. But you might have a branch which throws an exception unless it is never hit. So in our case, as long as this condition is never true, this function will still evaluate at compile time. But if this condition is not true, we will try to throw an exception, and this is the place where compiler will give us error. This comparison failed, so we are trying to throw this exception, and it will effectively give you the whole call stack. So you'll get very exact information what went wrong and where. And this is actually one of the key pillars to do this parsing. And after that, we just return the count. So if all the checks have passed, we just return the number of arguments expected for the format. Now, let's try to glue it all up together. So for the formatting, we said our structure will be a template of integer, and this is actually the most important part, because internally all we need to have is the pointer to this character array, because later on at runtime we will need to apply the format to the parameters, but back at that time we'll already know that both the format is correct and the number of parameters match expected. So even though this will be a runtime gluing up of possibly runtime parameters, it's still it's perfectly fine, because we know it's always valid, because it's validated at compile time. Now, how do we write it? And this is actually a part that I'm not really that proud of, because it requires us to define a template of a format, and this format needs to be like physically glued into two different locations. So first, we have our format structure just defined. Then we use our format check arity function, which we have been talking about, which will take format as a parameter. And this is also the place where we like explicitly enforce compiler to do this at compile time, because we cannot have a template parameter evaluated at runtime. So this piece of code will actually ensure that this will definitely be invoked at compile time. And then as a last element, we just put this pointer to the format as well. So the macro is just needed to put exactly the same string into two different places. Now, how the usage can look like? Well, first usage is simple. We are just logging. We create our format with a macro, and then we provide two parameters. So parameter $1 is answer, $0 is 42. So the output for a formatted string will be the answer is 42. Then similarly, we can use the same parameter multiple times, because the way we are parsing, we're just ignoring repetitions. But we cannot do something like this. $2 is $0. And this is the error. This is exactly the situation which will cause exception from our helper function to check the arity. Because now we have parameter 0, we have parameter 2, but we are missing parameter 1. So it definitely means something went wrong. Either user just missed some parameter, or we would need to force user to pass some dummy parameter just as a placeholder that will never be used. So it's pointless. So at this point, we'll actually throw an exception, because we are using two distinct parameters, but actually we are missing one of them in the format. So this is an error. And second error scenario is actually for the format which is perfectly fine. Answer is $0, so using one parameter and 0 the highest index, that's good, but we are passing two parameters. And this is the place where the static assertion will kick in, because the format will state one parameter expected and the size of arguments is 2. So it will just not work, and it will fail at compile time. Now, if you are logging a lot using this format, for instance, for the user interface, you might want to have a helper macro for that will take format, list of parameters, and then use log formatting and pass on the parameters further on, so that you have later on more natural and shorter syntax, which actually looks very like a printf, but is then safe in terms of the format the format syntax, the number of parameters, and type safety. So basically, there is nothing you can do wrong here, and this is actually the power of this interface. But unfortunately, it requires a little bit gluing with the macros. And the last thing I wanted to mention in terms of translations is why we even had this formatting in the first place. And this is because of translations and translations only. So our problem is that we have this string, pass the salt colon some $0, which will be the name, like pass the salt John, and the output should be exactly the same sentence but in a different language. So for instance, in Polish, it sounds a little bit more natural to put the name at the beginning. John, podaj sól. So with this format, we can actually do these sort of tricks, because from the format signature perspective, it doesn't really matter where the parameters are. We are only interested if the format is valid and if the number of parameters match between different languages. And from that point on, it's actually very natural. If we format, for instance, say we always provide format in English language, then we can actually do text-based indexing. So this format text that is put inside the code of your application can be used as a key, and the value can be the same string but in a different language. So you can do this mapping. And because the string inside the format is always the same, it can still be evaluated at compile time, and only at runtime we can switch it to an actual string with different language. But how do you actually extract this string? And this is something that is a little bit more hairy, actually. You need to grab through the code with looking for format macro invocations, or you can try to define a format macro that will do something else, like, for instance, display a warning during compilation, so we can then go through logs and extract all the strings. Or you can actually do something clever, like using Clang AST to actually parse the source code and then extract all the parameters to the format macro invocations. This actually requires some experience with Clang, and actually something the tool that you need to write, but it's also doable. But the most important part is that you should actually add it as a part of your continuous integration, because if you already have all the checks for your formats and for the string inside the build, then you can actually add to CI support to make sure that your translation is always complete, because thanks to this extraction you will know exactly which strings you need to match, and whenever someone adds a new format, this will actually be immediately evaluated by the CI, and then you can check if you have actually corresponding strings to all the other languages that you would like. So you are always 100% sure that your translation is complete and always working. And moreover, you can also do a check of this different languages translations at compile time with a separate binary. So we can again validate the strings if they actually match the original one from the source code. So again, this is something that you can automate to make sure that there will be no mistakes from that point on. Okay, so we are shortly approaching the end of the presentation. So the first message I would like you to take out of this talk is that this is actually not what log is about. Log is actually a data structure, and there is a great book on that. And the fun fact is that the book actually consists only of 50 pages. So it's really nice to read, and it's actually full of content. So it's like really compacted pieces of information regarding the logging. And actually it's written by the guy who was one of chief architects for LinkedIn. So you can imagine that he's working at really big scale infrastructure, so he knows what he's talking about. So highly recommend that lecture. But from our perspective, it's very interesting is one of the opening sentence. Logs meant for humans to read are sort of anachronism. And this is true. This is actually how we have done things for last we've done things in like 80s or 90s. But nowadays, when the logs are coming and they're like coming big, we have like megabytes, gigabytes of logs per second, and I'm even afraid to ask how many logs like Google have. Then we need to actually process them somehow, and we need to put the machines in order to keep a track on what's going on in our infrastructure. And in order to do this, we need to keep our logs structured. So it's not enough to actually have just a few common fields. We actually need to keep each and every element that we log in the structured fashion. So it needs to be machine readable so that we can use it as automation, and we can detect anomalies and we can react on them. And if you are interested in example implementation, as I said, I did it in C++. There is a basic utilities and tools library that I happen to maintain over time. It's written in C++11. It's open source since BSD revised. It's available on GitHub, so you can use it in your favorite projects, including commercial ones. And aside of the concept, but like a real concept, not the simplified version that just needed to fit in the slides, it also contains some extra things, so different integrations, for instance, with a Logstash and different output formats, and also a lot of checks in the background and automated tests. And the fun fact is actually the library is using Docker-based SDK to build, so you do not really need to install you do not even need to install a compiler to make it work, and just see and play around it. And if you're not really familiar with what Docker is or how to use it for the SDK for your project, I will do a little crypto commercial, probably somewhere around next year. I'll actually give a talk solely on that, so it will be more like a DevOps talk. But if you're new to the subject, this introduction actually can come in handy, and I'll also show a little tricks how you can use Docker to improve certain things, including embedded systems, but also for working with like real big scale systems that are running on the regular PCs. So even though like the implementation and all the code snippets I've shown, they were written in C++, and maybe aside of this macro thing in the background, actually the implementation is quite nice and quite natural, but the idea itself is very universal, and in fact you can implement it in pretty much any language, modern language that you like. And actually the nice thing is that if you are using the dynamic language that has reflections, you can even skip the part when you are writing manually these two-field info methods, because the reflection can do exactly the same thing for you. So you can automate these steps as well. And in C++, hopefully C++20 will also have a reflections. This framework can be simplified even further to require like zero attention from the user perspective. It's just enough to create a structure and put it into Logger, and everything else will happen automatically. Okay, so this I think will be all from me. So do you have any questions? Yes?
Can you go back to the definition of your format macro?
Format macro, okay. This shall be somewhere around here, I guess. This one?
Yeah.
Okay.
Have you considered user-defined literals instead?
Please elaborate.
What did you say?
Please elaborate.
Yeah, well, I am not a fan of macros, so...
Welcome the club.
Could you replace your construction of your format with a user-defined literal that just takes a string and returns a format?
Yes, actually, this is a really great question. I actually have worked on this with a friend of mine, and we spent like probably 2 afternoons scratching our heads how to get rid of these macros. And the problem is that the only thing that can be an output, maybe the other way around. When you have a template, the value that you can pass to the template must be a simple type, like integer, boolean, this sort of things. You cannot actually pass a structure as a template parameter according to the rules. So this is the problem, because if we actually skip that part, we could actually remove this part as well, because this format could actually be a template parameter as well. But it turns out that according to language rules, you can't have this const char star as a template parameter. I mean, you can put it, but only reasonable value would be a null pointer. You cannot like physically put a string there, and this is the problem. Beg your pardon? Yes, yes, hopefully, and I am actually waiting for this change because I don't think hopefully this has been voted. I think it has been voted into the draft. Okay, the comment was that it has been voted into C++20. Okay, great, thanks for that, and I really hope that in 3 years we can get rid of the macros.
There's also a GCC and Clang extension for those string things.
Probably we could use an extension here. I haven't checked it, to be honest, but this would actually make the code non-portable. But okay, if there is an extension for that, this would be a solution. Yeah.
My other question was,
yes?
Are you familiar with the FMT library?
FMT for formatting?
Yeah, or CPP
yes.
format.
It actually it actually uses the very similar concept for the formatting part, but this is just about the formatting. So like the talk was a little bit broader in the scope, but in this sense, yes, you could use the same formatting library here as well. And actually, because of this nice customization point, which I had somewhere in the slides, actually, because of this, as long as you can use your own favorite formatting library equally well, the only difference is that you will need to provide a two-field info for it, and that's pretty much it. So this also can be added as an extension. Yeah, but in general, the concept is pretty much the same. Yeah.
So what do we have the next question?
Okay, so 2 questions.
How does it relate to binary serialization? I mean, with similar templates and wrappers, you could just serialize arbitrary binary data because I see that it just is. I just don't see the other side. You know, here we have the serialization.
Yes.
But what with deserialization?
Okay.
And it's it's a hard thing to do and to maintain. So how do you?
Not exactly, because the hard thing, well, normally we have been talking just about this part, the log generation. So this is really the scope of the presentation, and the remaining part was just mentioned because this is actually probably a topic for I don't know, a separate conference. There's like really big pieces of knowledge on how to actually create the system for a scale. But the long story short is that you can, once you have a structure inside things that are generated here, basically this guy, the translation has almost nothing to do, just like changing one tree to another and putting it into the storage. So actually this is fairly automatic. When it comes to writing rules, you still need to write them manually because you need to know what you're looking for. But now this is only a semantics. You're not fighting with a syntax. You're not trying to glue up some regex expression that will just extract some numbers out of the random strings and hopefully it will be unique enough to not too much different logs, for instance. You will actually have a structure. So it's now up to you to come up with the semantics, how things should work. And also, because you have a structure, you are no longer interested in a position. So for for instance, if you have some random log entry which will contain have like 5 or 10 parameters, and you add another 10 parameters to it, that's perfectly fine. That's a non-breaking change because you have just added extra parameters to the log. You do not need to change anything on the infrastructure side. You could argue that if you remove something, then you can break the other systems. Yes, this is true, but this is the semantics. In the same sense, if you remove all the logging altogether, you would also break it because it's like a change of semantics in a program. You are actually physically giving a different type of information out.
Okay, thank you.
In a way, you can think about it actually as like the whole concept. Actually, logging is a sort of a messaging system here. Because you're creating messages about the events. It's just like a unidirectional channel. You just send out the pieces of information for the processing. I think there was one more question, yes?
Your field structure was a dynamic.
Yes.
And is it just too slow to generate each log such a dynamic structure?
Okay, so the question is basically about the speed. Okay, log representation. So let's get to this conceptual part here.
Yeah, you have vector of fields.
Yes, this definitely will be allocated on a heap. So yes, it does means allocation is there. It's not necessary needs to be there. So for instance, if you have a simple type for like int, that's just put in place. But in general, yes, it will. It might cost you a runtime. And in general, also, the bigger structure you log, the deeper the tree is, the more allocations you will have. But this is actually also one of the design decisions. Actually, I gave a talk about this logger something like 4 months ago or so, and it was actually shaped a very different way. So there, the structure was pretty much a key value and it was flat. And the nice thing is that with a little bit of trickery, you can avoid like 100% of memory allocation. So no memory allocations at all. It was blazing fast. But actually, it was limited because you couldn't really reasonably represent structures which are nested. So for instance, like this vector, how do you represent it in a key value form? You can, of course, agree that there will be a certain format, that the string will represent a JSON and so on. But then you do not really have a unified representation across all the things. So while it's technically doable, and for some systems it definitely would be a good idea, it was just my design decision that I will actually go for something more generic at a little cost of the runtime. And the reason behind it was actually, before I even started to do any benchmarking, I realized that like most frameworks are actually just selling you, we are fast. We're doing like 10 billion gazillions of logs per second. But actually, what does it mean? They give you millions of useless logs per second. So maybe it would be worth to do it the other way around. Instead of doing millions of logs, do some, I don't know, hundreds, thousands of logs, but make it reasonable so that you can actually play around with it. You can integrate. You can, for instance, do the statistics and logging at the same time. And actually, for simple logs, it's not really that bad. Even for logs which contains like some tens of parameters, you can still generate logs much faster than logstash can consume them. So in this sense, it's not really a bottleneck. In general, yes, do not expect this logger to be as blazing fast like other, say, top 10 fast loggers on the market. But on the other hand, you get something that none of these loggers have, the structure that you can browse easily.
I think we have time for one more question.
Okay.
Coming.
Hello, and first thing first, thanks for your awesome talk. The question is, so I'm using a logger that uses a printf style logging as well, and the real question is, do the objects in log really have to be enumerated, like $0, $1? Wouldn't it be easier to implement and use if they wouldn't be enumerated?
Yes, this was actually one of the ideas also at a certain point, but there was actually one big problem called a translation, and actually this is the part. If we are only putting positions, then in this case it would work because it's the same parameter. But if a different language, you would have two parameters, and different language you would need to swap the order. This actually would be impossible to implement this way because it means you would need to change them in a program as well. So this is why I opt in for using the numbers. But this is actually a great question because this is the sole reason why we have even the numbers, because otherwise the syntax would be even simpler.
Okay, that makes sense. Thank you very much.
Bartek,
Okay.
do you have any closing remarks, or are you ready to take the applause?
Okay, I guess we are running out of time, so maybe I'll just not take the slot for next speaker. So thanks for listening, and I hope you'll find it useful.
Bartosz Szurgot.